Today we've got Professor Knox in the Electrical Engineering Department to give you a great presentation on ins and outs of electrical engineering, so please give him a warm welcome.
So good afternoon. So they tell me my job is to convince everyone here to become an electrical engineer. I don't know. So far I guess I was up against any civil engineers in here? Really? No? All right, so my job is done. Computer science, that's a lot. Okay. So any EEs, any electrical, straight electrical engineers. All right, excellent. All right, so then I also here next week is computer engineering. So the department I'm from, we do what? We have electrical engineering and computer engineering. Some students gravitate towards computer engineering, some gravitate towards EE. My background is straight EE. I'm also, it's Tandon, but I'm a poly grad. The school was called Polytechnic before it became Tandon a few years ago. So it was a long time, but I also graduated from here as well. So I do have a lot of cables and buttons and things to push. So I'm hoping that it doesn't turn into long-term disability and tripping on something. But I'm going to do a lot of live demos today. So we're going to be looking at screens of test equipment. We also have a small robot system that's going to be running around the lab here, and my research assistant Ashton is going to be sort of operating that robot. We'll talk a little bit about aspects of electrical engineering. So from an outline point of view, just to get you in the mindset of what an electrical engineer, the tools and the modes that they try to work in, we're going to be talking a little bit about signals in the time domain, and then relationships to those same signals in the frequency domain. And as an electrical engineer, we kind of always have our feet in both of those domains, though we tend to be comfortable in one versus another. So some of the demos we'll be looking at, I'm going to pull up some instrumentation. We're going to be able to measure cellular signals, Wi-Fi, Bluetooth signals. The Beacon project is part of this robot thing here. I'll describe that in a little while. And then I'll also do an RFID demo for you before we go. So we try to pack a lot into the 1 hour that we're here. But as we move on, we'll answer these two questions later. But I want you to start thinking about if you were standing in the jungle, if you ever had an opportunity to do that, it'd be great. If you watch a movie or you see something. Usually the sound effects in a movie in the jungle is very noisy, but that really does duplicate what's going on in the jungle. There's a lot of birds and frogs, and they're all kind of chirping and barking, and well, I guess frogs don't bark, but they're making noises all simultaneously, and yet with all that happening, they're still able to communicate over very large distances. So one of the questions would be, and it kind of relates to what we do as electrical engineers, is well, how is that possible? How are all those different species of animals able to communicate simultaneously? The other question would be, and we'll answer this a little bit later towards the end, is can your keys that you carry around in your pocket, can they communicate? Like, is it possible that your keys somehow could talk to you? So we'll try to answer both of these as we move on. So first we're going to talk a little bit about time and frequency domains. So what we have here is all the waveforms we look at are all going to be amplitude in the vertical. So this is the amount. You can think of it as, like, in this case, it's voice. It's the sound level, so how big the sounds are in the amplitude. And that goes for both the frequency and time domain. So the top waveform is time. So as time progresses, I'm talking right now about a microphone, and I put that microphone on some instrumentation. I can see the sound waves of my voice kind of moving along in time. Now, if I also, and most people would be comfortable with that, because we live in time, right? Time always marches forward. We have an idea of what time is like. But we can also look at this in the frequency domain. So frequency along the bottom here, we have low frequencies down here, so this is all your bass tones. And then the high frequency up here would be maybe an opera singer with a very high voice. So I can also look at those same waveforms in both time and frequency. So for instance, if we look at the frequency domain, evolution has it that as we start to speak louder and louder, the frequencies in around 1,000 kilohertz tend to be dominant. So my guess is, if evolution is correct, our ears are more sensitive to around 1,000 kilohertz, so that we can hear people far away. I mean, this is 100,000 years of evolution. So, but when we're talking in a casual voice, the amplitude is relatively flat across the frequency domain. So now for you, so how, we'll take this a little further. So if you're at, let's say you attended an opera. Anybody go to an opera? Oh, wow, well, some classic people in the audience. Did you, I guess the question is, did you sleep during the opera? I don't know. So if you've gone to an opera, you know what an opera is. There is a live orchestra playing music, and then there's the opera singer that comes out. And what opera singers try to do is put the frequency of their voice higher than the orchestra is playing. Now, most of the instruments in the orchestra are about 800 hertz and lower. So when the orchestra plays, they're operating down here in the frequency domain, and when the opera singers are singing, they're trying to get much higher, so that you, as the observer, you can hear both of those signals at the same time. So this is sort of how we're separating things in the frequency domain, which you wouldn't be able to detect in the time domain. So just to review a few things. There's from an engineering point of view, there's, as a function of time, there's something we call direct current, DC. You're probably familiar with it. You're all carrying around DC devices in your pockets. These are your batteries, right? So as a function of time, there is absolutely no change to the waveform's amplitude, right? It just sits there static. Eventually, your battery is going to die, and this eventually is going to start to fall off. But over a short period of time, it's relatively flat. And in the frequency domain, again, we're going to be comparing time, things that happen in time, and things that happen in frequency. In the frequency domain, there's no frequency content here. There's nothing changing. There's nobody singing. There's nobody playing the piano. So all the frequency is all centered at 0 hertz, right? So there's no changing in frequency at all. So I would, as an engineer, if I'm trying to design a system, I always have my thoughts in both of these at the same time. So what are our DC sources? Obviously, a battery is truly a DC source. There is no variation over time other than eventually the chemical reaction starts to decay. But all of these you're quite familiar with. You're probably carrying around 2 to 3 of these in your pocket. You're always looking for the plug-in. Also solar panels. These are actually converters. They start off with a time-varying waveform, like light, which is sinusoidal. It's a time-varying waveform, and they convert it to DC for you, because our electronics generally works in DC. So electrical engineers would design some of these. Generally a chemist would design the battery. So again, no change over time. Things get a little more interesting though when we look at time variation waveforms. Things that change in time. So this is you'll take some physics classes and things. They'll be showing you this as well. This is what's called a sinusoidal waveform. It's sine omega t. You're probably familiar with sine omega t. So in this case, this again is time. And this is a sine wave. Its amplitude increases, and then it drops, it goes negative, and then back to 0. So this is, and then it repeats. So this is one period of the waveform. In this particular example, I'm saying this is 0.001 seconds or a millisecond. And I might be interested in this for a variety of reasons. Again, time domain. Now, I can also convert this to frequency, taking the inverse of time. So you're going to learn this, if you haven't done this already, you're going to learn there is a intimate relationship between these two. They're inversely related. So if I take the time, I just take 1 over that, I get frequency. The units that we use is hertz. This is from the engineers Hertz who identified this. So in this case, this is a 1 kilohertz tone. So we can hear this. Our ears are tuned that we can hear as low as 20 hertz, and we can hear as high as 20 kilohertz. And then generally our hearing then starts to drop off beyond that. Now there is some theory, I don't think it's theories, I think it's well known that animals can hear higher than 20 kilohertz, right? Because they have these things called silent dog whistles. You can blow into them. And a dog would hear that, but we wouldn't hear anything. So evolution has them, for some reason, able to hear higher frequencies than we can. But again, so this would be something that we could hear. Now, in this case, if I look at this sinusoidal waveform in frequency, here's our sine wave here going up and down, and here's our frequency domain. If this is a single sine wave, I would just see a single tone, one frequency, and this would be, from the previous example, this would be 1 kilohertz. So what I'm going to show you shortly is I'm going to show you instrument displays that measure waveforms in time, and I'm going to show you some that measure waveforms in frequency. Now, today a lot of my talk has to do with wireless communication, and wireless people tend to think of everything in frequency domain. They think less about time waveforms. But if you were designing a gaming computer, any gamers in the audience? Why don't we get to hearing aid, right? So if you were the engineer designing that, and I guess you build your own PCs, right? You don't buy, like, everything's a custom build. But if you were designing a microprocessor, you're Intel or AMD, and I guess you could argue a gamer which processors are better. You think everything in time domain. You're looking at these digital waveforms moving as fast as they can between memory and the microcontroller, and these ones and zeros moving as fast as possible. So those engineers tend to think in time domain, and I'll show you shortly why. Wireless engineers tend to think in the frequency domain. So what would be some sources associated with this? Obviously the sun, any light source, those are sine waves that are coming out. Those sine waves have to be very high frequencies, and our eyes can capture those. These other devices here, obviously, you know, the wall socket, that's a 60 hertz sine wave that comes out. There's some history of why that was generated, why it was selected to be 60 hertz. This is a piece of test equipment, a function generator. I have some of these up here as well. And then we'll just look at, radar systems. We're going to talk a little bit later. And then cellular base stations, which is how you get all your Instagram or Facebook. If it was my generation, it was MySpace. Anybody know what MySpace is? Yeah, a few people, yeah. Anybody use MySpace? Yeah, you still use MySpace. Is it coming back? We're bringing it back? No. I'm so excited. I think I have MySpace. There's some pictures somewhere out there with me. All right, so let's look at a base station. So I mentioned earlier, kind of a hint, how do all these animals communicate at the same time? So when you're making a cell phone call, they want it to be as fluid as this. Now, right now, I'm doing all the talking. You're really not talking. But if you're having a conversation with someone, it's kind of what's called full duplex. You can interrupt each other. You want that. It's a natural flow of communication. So they wanted that with landline phones, which you have, right? You can interrupt someone on a landline phone. And also with cellular. Now, how do they do it in cellular? Is they essentially split the frequencies into two separate bands. So in this case, when you make a cell phone call, let's just say cell phone call this way, because it is someone talking, you can talk. You're assigned two frequencies. So one frequency is somewhere in the band of what I call the uplink, and there are some frequencies in the downlink. So they're actually assigning you two separate frequencies when you first register to make that phone call. And what they're trying to do is, they said, well, we know we can't communicate on the exact same frequency because we'll interfere with each other. So we'll put the call from your phone to the base station, the uplink, at one set of frequencies, and we'll put the call from the base station to you at a different set. So that allows full duplex, allows us to simultaneously communicate at the same time. So this is what an electrical engineer would use. One of our tools is we have a lot of frequencies, let's split up frequencies in different places. So now another thing is, this is a cellular application. So here I am in this cell, and right now I'm communicating to this base station here, and I'm walking along the street or I'm driving my car. I only have so many frequencies available. As I make this motion to go into the adjacent base station, there's a process called handoff. It's pretty seamless to you. One base station hands your call off to another base station. A lot of times you don't even know what's happening. And you're reusing those frequencies again at the adjacent base station. So this says, so not only can I use frequency as to my benefit, I can also use space, physical distance, to allow me to then reuse things that I used before. So this is how a cellular system works. So we'll do the first demo. Let's see, there's a lot going on up here with the cables and things, so let's see how this will work out. So what I'm showing you now is an instrument called a spectrum analyzer. And what this does, this measures frequency along the bottom axis and amplitude in the vertical axis. Oh, great. Okay, so there it is. So you can see along the bottom, right now, there's just some noise bouncing around at the very bottom, and it's gone. Okay, so again, so frequency is along the bottom, and All right, so you see this little, you all got to look at this tiny little screen over here. All right, so we'll try one more time. I don't want to speak because I'm afraid that's that was unbelievable. My screechy voice. All right, so we may have to come back to that. All right. Oh, look at that. Oh, oh it's not going bad. All right, I'm going to move it over to another piece of equipment and hope for the best. Maybe just that one doesn't want to be friendly today. Okay, this is a little bit better. So, all right, so I'm going to switch. That looks good. So I'm going to hold that for a second. I'm going to go back and set up the next demo. So I'm skipping over the cellular demo for a second. We'll see if we can get back to it. And now I'm going to go back to the slides. I want to set up the robot demo up here, which is the next one. All right. So so what we have here is my Rover. It's when you first look at a robot, your first impression is, oh, well, this is mechanical engineering, right? This is a mechanical engineering project. And part of my pitch today is to show you that there's probably a lot more electrical engineering in the small robot than there is mechanical. So I know a lot of students come to college and they're like, you know, they see these cool robot shows, movies, whatever it is on YouTube. They're like, oh, I want to do robots as a career. And I would argue that, yeah, you could also be in the robot business taking electrical engineering as well. So the setup here is this rover here's job is to find one of these two beacons. Now, what's in the beacon is they're making two different frequency sounds. One of them is a 5 kilohertz tone, and one of them is an 8 kilohertz tone. Now, we can all hear, this is the frequency range we can hear, so we're going to be able to hear those two tones. And the robot's job is to go to the 5 kilohertz, right? So we're going to, in a few seconds, as part of the demo, we're going to turn the rover on. The rover's job is to listen with its internal microphone and try to identify which was the 5 kilohertz beacon, and then drive to that one and stop. Now, if we're unsuccessful, I guess Asha will get an F for the class, or so this it all relies on how well she does today on this robot demo. And then what we'll do also, we're going to show some slides. So let me just show you a little bit of what's in the robot, and then we'll then actually see if we can get this to work. So here's what. So this is the circuitry, the electronics that's in the rover to make it work. So one thing we have is this structure. I call it the cone. There was a 3D printed device to kind of narrow the focus of the sound waves being captured. We didn't want just the microphone capturing all the sounds, because without directionality, we have no idea where the sound's coming from. We actually, as a human, we do a great job. We have 2 ears, and our brain can detect slight delays in the same sound in each ear, so we can kind of know directionality. But this robot only has 1 ear, effectively. It has to try to find something. So the first one was this 3D printed cone. The sound wave comes in. We have a standard microphone. Now, a microphone is a converter device. It takes a sound pressure wave and converts it to an electrical signal. Then the robot captures the electrical signal, sends it into a small Arduino-type microcontroller. In this case, it was a Teensy. The Teensy is the brains of the operation. It measures this signal. It also, at the same time, sends out, has an ultrasonic sensor. It's constantly looking not to bump into things. We don't want it to crash into these beacons. When it gets close to it, it's supposed to stop. So this works as a mini radar. It sends out an ultrasonic signal that we can't hear. the sensor associated with here, but there is a 40 kilohertz signal that bounces off the object, comes back in. That's captured by the teensy. It's listening, it's measuring its environment with ultrasound. We got some cool lights blinking on and off, kind of just tells us how things working. And then it drives the motors. So then as it moves around, it's kind of changing its direction, and it's using that cone to kind of probe the environment, and it's looking for the loudest signal. Once it finds it, it then drives in the direction towards that. So all of this, the motor driver, it's a board that sits on top of the microcontroller, and the motors themselves, all designed by EEs. So the structure of the device, I don't want to downplay any mechanical engineers in here, but the structure of the device and how much weight it can support and those things, that would be a mechanical engineering design. But all this, I was almost using the word intelligence, but then again I'm downplaying. Where's my mechanical engineers? I don't want to insult, so please, am I insulting you? There's a lot of intelligence in the mechanical stuff, but being an electrical engineer, I'm kind of partial to how cool the EE stuff is. But anyway, so all this stuff again is all designed by EEs in the system. Now the beacons themselves, all these are just oscillators, and they just have a small speaker, and they're just beeping out at either 5 kilohertz or 8 kilohertz. And then again, then the buzzer comes out, and then this is what is used to identify which of the two beacons. So what we're going to do is for this demo, and as long as we can get our equipment screen back on, the two beacons are going to flash. One's going to flash 5 kilohertz, one's going to flash 8. We have a microphone here, and we're going to put all of this into an instrument that measures amplitude as a function of time. And we're going to see, the robot's going to do its thing. We're going to talk a little bit about the waveforms. And again, whether I'm going to let everybody, we'll have you decide if Ashley gets an A or an F at the end of the demo. So, not too much pressure on you. So I'll be able to adjust this up here. Yeah, I think we're good. All right, so the 3 waveforms you're looking at, this is time. Time is marching on. The upper waveform, I think we lost the oh, there it goes. Okay, so the yellow waveform is all on one channel. So what we're seeing is amplitude changes. When that beacon is on, you're seeing this burst of signal. In other words, this is the first 5 kilohertz beacon. Its energy is here, and then it shuts off. So you're hearing it on, you hear it off. And if I'll stay quiet for a second, you can hear these 2 beacons going back and forth. The green one here, the lower one, that's the other beacon. That's the burst of sound at 8 kilohertz. And what we're seeing down here is the blue one. This is the microphone. Now, the microphone's also picking up your background noise, me talking. So right now it's kind of messy, but so I'm going to be quiet while the robot does its thing. So Ash is going to turn on the robot, and it's going to now start to scan around. Its job is to look for the yellow signal, the 5 kilohertz, and drive over to it and stop when it finds it. So I'll pause. We'll see if it works. You did it. Now, if it crashed a little, I was going to say drive like my wife, but I'm sure my wife will smack me. So drive like me, I'll leave it at that. My wife's actually learning to drive. My wife's also a polygraduate, much smarter than I. All right, so right now, I mean, if you listen, you can kind of hear, like with all the intelligence of your brain, you can kind of hear the 2 different tones, right? One's a little lot louder than the other one. And because they're separated in time, so as an engineer, this is a trick I can perform. I can make sure that only one beacon is on at a time. In other words, I synchronized our system that only one is on. So you can almost, I can have one of you come up and you can kind of hear the one, I can have you walk over it, and it would work. I think you would be able to do that. And right now it's easy for the robot to do this in time. The question is, what happens if I lose control and the two beacons are not connected in any way, and they just arbitrarily just start beeping? There's a chance that the two of them can line up. And then we can possibly have an interference. It's going to definitely be harder for us. So we'll go into that mode now. You don't have to have the robot go, but I just want you to recognize this other mode. So now both of them are on at the same time. Now I'll have you listen and see if you can tell me, is there two signals now or one? You know, is it because they're pretty close also in frequency. Yeah, I don't know. Is anybody that good? Could they hear that there's still two happening at the same time? Or you can lie if you want right now. And maybe, all right. So much harder to distinguish, right? To have that. Now for us, it might sound a little nicer having two tones. And that's really, you know, piano playing and guitars. You know, it's usually many frequencies together. It's a little more pleasant. But for the robot, how is the robot going to figure this out? Like it sees. Its microphone captures both at the same time. So here's where an engineer would move into the frequency domain. Let's see what happens in frequency and see if that would actually use it to help the robot. So I'm going to pull up another file here. So I had saved instrument states here. So go back to the other mode first. So here's the previous mode where only one is on at a time. Now what we're looking at here in the purple display is this is frequency now. It's no longer time, it's frequency, and it's amplitude. And this is the first mode where only one's on at a time. So you can see frequency popping up. There's a frequency here at 8 kilohertz. This is higher frequency here. This is 8 kilohertz. And this is 5 kilohertz. So you can see they're popping back and forth. Now let's go into the mode of where they're simultaneous. Both of them are popping up at the same time, but I can design an electronic filter, and I can filter out the 8 kilohertz. I can actually have a device that removes this energy, and I just focus on this energy. So what we're looking at here is something, a mathematical formula. It's called the fast Fourier transform. It takes time waveforms and very easily mathematically change them into frequency. And then I can give this to the brains of the outfit, the microcontroller, and say, you know what? You now filter out and just don't even think about the 8 kilohertz one. Only focus on the 5 kilohertz and use that to drive your motors. So that's how this thing works. So, okay, so I think we're good with that one. Yeah, I guess you could probably shut it all down. So let me switch back to presentation. Oh, you want to do this with frequency tone? Okay. You should have quit while you're ahead. So, all right, you can shut it down. I appreciate that. Thank you very much. So, I gave a round of applause. So I'm going to go back to that question I asked you earlier about how all these birds and animals and frogs in the jungle, how do they all communicate? So essentially what evolution has done is they've set different bird species and frog species at different frequencies. So they all chirp at different frequencies. So like we saw earlier, where we had the beacon sort of simultaneously transmitting, birds are tuned in to only listen to their own species. And the way it's separated out is evolution has them all sort of assigned to different places. The frogs are a much lower frequency, certain birds have much higher frequency chirping. So that's how we're all able to communicate, or they are able to communicate simultaneously. The other thing, so they're really, so as an electrical engineer, we're kind of leveraging what evolution has already figured out for us, but we use the same things. So what they do leverage is time. They could, I'm sure two birds aren't talking at once. One bird chirps, says, here I am, I need a date this weekend. And the other bird says, yeah, I'm not available, I'm attached to someone else. check my Instagram, right? So I can do this with time, I can share in time. Obviously I can do frequency, I mentioned, everybody's evolution has a different one, but also space. You don't necessarily have the same species in different places. I'm sure there's some species that migrated to the very tops of trees for some reason, maybe to get away from all the noise. And obviously the frogs are way down, so they also use the same techniques. So this is all available to us as well as an engineer. So let's look at a communication system. I may go back to the previous, you know what? So let me go through these slides, and I may go through the cellular. I'm going to try to get back that equipment again. But let's look at another way of communicating. So right now you all have active transmitters. Some portion of the time when you're asking for a website or you're making a phone call, you're sending a signal out. You're actively sending sine waves out that have information encoded or modulated onto those sine waves. And that's how you're able to communicate, by just sending out an active transmitter. But radar works slightly different. Radar says, well, I'm going to send out a signal, I'm going to let it bounce off my target, and my own signal is eventually going to return to me, and I'm going to measure that signal. So in this case I'm showing a plane, that's really a passive transmitter. It's not trying to communicate, it just happens to be metal, and anything that bounces, the energy that bounces off of it is returned back. So that could be a good thing or a bad thing, depending on the application. So again, so I can communicate just by what's called reflective signal, reflective communication. So one of my favorite movies is James Bond. Now I'm an old guy, so I'm the Sean Connery James Bond. A lot of you may not even know who Sean Connery is. Daniel Craig, you know Daniel Craig? Yeah? Okay, yeah, so you know Daniel. Anybody know Sean Connery? Oh, okay, so we got some Bond fans in there, okay. So the earlier Bond movies, I don't think Daniel Craig's too cool for this, but the earlier Bond movies, Bond would walk into his apartment, and the first thing we do is pull out the little device, and he's carried it around, and he's looking for what's called a bug, a transmitter, right? So he's got, essentially it's like the equipment I have up here in handheld form. He's looking for energy being transmitted. Essentially, it's a microphone somewhere in the room, because he knows the enemy's trying to listen in on him, and of course they gave him the one hotel that has the bug. It's usually up. Where is it? It's usually up high, like in the lamp at the ceiling, like as if you wouldn't look there. So in that case, that's an active transmitter. So the bug, the device itself, has an antenna, has a transmitter, a microphone, and a battery, and it is sending out sine waves into space. And old Sean Connery, or the 007, is a receiver, and he just measures that energy, and he says, oh yeah, the bug is there, he takes it out, and he's trying to think of what was, well, this one was from Russia with Love, that's where the image came from, so he usually drops it in a glass of water or something, something to get rid of, flushes it. I don't think he flushes it down the toilet, that's probably too cool, uncool for James Bond. So obviously, so transmitters. So now let's take it to the real world. So spy situations happen in the real world. So if we look at this device here, this is this plaque that was given from the Boy Scout equivalent in Russia. They had given it to the U.S. Embassy in Moscow. So there was a building created in Moscow, the United States, after World War II, and we still have them. They were called ambassadors. They send them to that country, and these individuals stay in that country and then report back negotiations and things. So of course, at the time, we knew about these active transmitters. If they said, so I'm Moscow, I said, oh, here you go, U.S., here's your new building, move on in. I'm sure the first thing they did was, just like James Bond, they looked for bugs, they looked for transmitters, because I'm sure Russia would just love to hear the communications between the U.S. ambassador and the president at the time. So here's this device. It's a carved wooden plaque. They checked it out. It was not transmitting energy at the time. It looked perfectly safe. And it hung in the U.S. Embassy in their den for 7 years. So again, not transmitting anything, at least when they checked it. It was actually a pretty ingenious device. Inside, as not an active transmitter, there was still a microphone, and there was an antenna device. So how this works is it's sitting again in the U.S. ambassador's office. Across the street, the Russian agent turned on a transmitter. The transmitter was pointed across the street to the U.S. Embassy. The energy bounced off of this thing, and vibrations of the microphone inside reflected energy back. It was like a mini radar, but they didn't know what was happening. So anytime you come in and you try to see if this thing is sending energy, they just turn off the ones across the street, just sit there, have some coffee. As soon as they leave all the equipment, they turn it back on, and they're listening to everything. So it wasn't until after 7 years that they finally bust this thing open, and they found this very unique device buried inside. So the device itself sits down. If you're interested in spy, things, there's a really cool museum in Washington, D.C. called the Spy Museum, and this device is hanging there. They actually have it turned around so you can see the back of it and how it was created. The engineer at the time they created it was this individual called Theremin. Anybody know what Big Bang Theory? The main character played some musical instrument called the theremin. Does that sound familiar to anybody? Yeah, right? So the theremin is named after the inventor of that musical device, but he also invented this thing as well. So again, I can use reflected energy as a communication vehicle. And you actually, everybody here, I know for sure, you all have a reflected communication device. You're carrying one around with you. The Russians didn't put it there, so don't start running out the door. But it's your, did anybody know what it is? Yes, what? NYU ID, exactly right. That's what's called an RFID tag. This thing does not transmit energy. We're not tracking you all the time. When you come close to the guard booth and you hold it close to the guard booth, the energy from the guard booth lights this thing up. Then the little eye, there is an eye seen here with a unique serial number. This starts to reflect energy back and essentially tells the guard booth that, I have an ID, and then the ID is run through a database, and then the database says, I guess whether you paid your bill or not, or whether you should come in. So again, that's an RFID system. So what I'm going to do now is I'm going to try to switch back to my demo with the equipment, the other instrument, and see if we kind of resolve the issues. Okay, I'm always afraid to talk at this point. I feel like Bill Gates with the blue screen of death. I don't know if you've heard of that. Yeah, just kind of do that. Yeah. I'm going to try one more thing. Okay, maybe. All right, so what we have set up here is a device called a spectrum analyzer. So what the spectrum analyzer does is it measures amplitudes of signals as a function of frequency. So I'm backing up. I'm going to go to the early part of the presentation just to start it off, and then I'll show you an RFID tag. So what we're looking at here is along the bottom axis is frequency. Right now the center frequency is 915 megahertz. and I'm looking at just slightly around that. And right now I don't see anything. In other words, I just see some noise bouncing around. So the signal's pretty clean. And what I'm connected to here is I have a sine wave generator that's just sending out a single tone, a single sine wave at 915 megahertz. It's 915 times 10 to the 6 hertz sine wave. So it's a very rapid sine wave. It then is amplified and it's sent out through this device here. This is an antenna that's just sending energy out in this direction. So, I'm going to turn on the sine wave. So as we showed earlier, a single sine wave just shows a single tone. It's just a spike straight up. And that's how strong the amplitude is. Now where it's being received from, this is my transmitter, so this is an active transmitter. We're not up to the RFID yet. It's being transmitted from here, and it's being received on this device. This is called a horn antenna. This is very directional. It's capturing energy, kind of like the cone on the Rover here. It's capturing energy only in a cone. So it wants to see energy in this direction. Now in this case, I'm pointed over here. I'm still seeing energy because this is kind of bouncing around the room. RF energy bounces all over the place. RF being radio frequency. This is what I'm calling this frequency. But if I turn this directional antenna towards that one, you'll see the amplitude pop up as I get closer to this one. So I can use this as a form of direction finding. You see the signal is getting much bigger. And as I get closer, it gets larger and larger because I'm capturing more of this energy. Again, if I point away, even with me standing between the two, I still have some energy because it's bouncing off the floors, the ceilings. You're absorbing a lot of the energy. I'm absorbing a lot of the energy. So it's much less amplitude. But again, this is an active transmitter. This is the receiver. So before we get to RFID, I'll back up a little, and we'll look at cellular signals because I think in some cases those are interesting as well. So let me just turn this one off. So this same antenna will allow me to capture cellular signals as well. There's a lot of cell signals in here. I'm sure most of you can make a phone call right now. It would all work. And what you're seeing here are the different uplink and downlink frequency bands. So there's two small markers here. I don't know if you can see these. There's a marker 1 and a marker 2. These are the cellular bands for the uplink. And every once in a while you see something's peeking up in here, something popping out of the noise. This is all the noise floor of the instrument. So anything above this level is a measured signal. So I'm seeing some stuff popping up. This is the uplink. That means someone in the room is probably texting someone. So Big Brother's watching. So where are you? Should I walk around and see if I can find it? So 1 to 2 is the uplink. Oh, now everybody's getting involved with this, right? And then the bands here, there's a marker here, 3 to 4. You see, this is on most of the time. This is the base station energy. So somewhere in this community, there's several base stations. We're near probably the closest one is what we're measuring. Base stations tend to transmit all the time because they're talking to many, many users, not just the ones in this room, but there are other users outside, out in the atrium and buildings around. So you see there's a lot more base station energy in the downlink, and occasionally someone's doing something in the uplink, something's happening. If we were to actually make a phone call and stay on the call, this would be more steady. You'd see a signal pop out of here and stay here. This is very bursty, so it's something quick. It's a request for a web page, it's an Instagram photo upload, it's something happening very, very quickly. Or if you're MySpace, maybe that's a MySpace upload to some other old guy in some room somewhere. So this is the cellular bands. So let's look, the ones that you're mostly interested in, because I don't think any of you actually make a phone call. Have any actually made a phone call on a smartphone? Oh, a couple of people, all right. So you called your parents, right? I need more money, right? You figure that's better than a text. I would think that's probably better than a text. So let's look at Wi-Fi, because I think most of your activity is sitting up in the Wi-Fi bands. So this is the Wi-Fi band. So I actually just changed the frequency in the instrument. I said, well, I'm not interested in cellular anymore. Let's move to the frequency of Wi-Fi. Wi-Fi is higher. It's 2.4 gigahertz. 2.4 gigahertz to 2.48 gigahertz. So that's what we're seeing here. See the instrument set up at 2.4, and then over here is 2.485. So that's the frequency band that's been assigned by our government. The Federal Communications Commission has assigned these frequencies to Wi-Fi. And there's a lot of activity here. So this actually might be more of your Wi-Fi communications. And then there's some stuff going on. It's all very bursty because most of this is data. In these bands, you're only allowed to transmit very quickly. You have less than half a second. You have to turn off your transmitter. Let me try one thing. See if we can sort of detect the maximums. To see if we can start to identify, over a period of time now, capturing all the maximum amplitudes. And there's a lot of activity here. You can see there's sort of this big blob here. There's another one here. This is the Wi-Fi. When you send out an energy, you're sending out a lot of frequencies at once. But you don't do it for very long. So that's this. You also see these small little spikes here. These are Bluetooth signals. Wi-Fi and Bluetooth coexist in the same frequency band. And it's been designed that they don't interfere with each other. So this is Bluetooth. A lot of you have smartphones that may have your Bluetooth on, though most of you probably turn that off for battery conservation. But that's what's happening here. So there's kind of a mix of Wi-Fi and Bluetooth at the same time. All right, so we'll leave that. So let's go back to RFID. Let's go back to the RFID case. Any questions on this? I don't know. I don't know. Is it possible you can take questions? Anybody got any real general questions you can scream out? Nothing? No? EEs are the best? Yeah, I heard that. Yes, I heard it.
Do you do any research?
I'm sorry?
What type of research do you do?
Oh yeah, so the question was about research. So I'm connected to the Research Center NYU Wireless. So NYU Wireless, right now we're looking at 5G. Everybody, the majority of you right now are carrying around 4G phones, right? You probably see 4G show up on the phone. So we're now trying to decide, well, what's the next thing that's doing it? And it's always, the next generation is always more bandwidth, more data. I want 4K YouTube to stream to my phone. Well, you can't get that with LTE 4G, so they're trying to say, well, how can we do that with 5G? On the big picture specifically, it's 5G research. I'm doing something called specifically more what's called full duplex communication. Remember the uplink and the downlink example? There were two separate frequencies. So that means when you make a phone call, you're really using twice the frequency resource. Every single bit of frequency is spoken for. So if you're using twice, is it possible that you can communicate both up and down at the same frequency without interfering with yourself? And right now that's been the thrust of my research. But after the talk, if anybody's interested, you're welcome to stop up, and we can talk more specifics. All right, so let's look. So we still have a few more minutes left. Let me switch back to the RFID example. In this case, unfortunately, I got to switch to the other instrument again. So give me a second to see if this one works. Seem to have more success with the time domain instrument for some reason. Oh, I'm sorry, was there another question? Nothing? No? Okay. What then? Oh, I'm sorry, something in the back? Oh, that's an excellent question. So the question was, what's the difference between 5 gigahertz Wi-Fi and 5G? So Wi-Fi bands, the band I showed you before, was 2.4 gigahertz. Gigahertz is the frequency, it's the sine wave that's actually transmitted. So when you talk about Wi-Fi at 5.6 gigahertz, that just means that the carrier frequency is higher. So effectively what happens is you make a Wi-Fi signal, you're negotiating with the access port, which is somewhere up here maybe, or maybe out in the hall, and the access port is telling you it's better for you to work at 5.6 gigahertz. It's essentially moving you to a certain frequency to communicate. Completely unrelated to 5G. The G, they're both 5G, it's kind of confusing. The G in 5G is generation. So right now We're at the 4th generation of cellular technology. 5G is the 5th generation. So it's really just, it's usually like a decade. Usually it takes about 10 years for cellular. So I'm old enough, I lived through 1G, which was the first cellular system. We used to essentially carry the mobile phone back in the 80s was essentially a suitcase. You carry around another suitcase with you. And everything was in there. There was a huge antenna that you'd mount on the top of the car with a magnet. And that's how we communicated. As time went on, they moved to 2G, 2nd generation cellular. That's when they made the switch to digital, and we've been digital all along. Now, what do I mean by digital? Is we're officially voice. We're taking your voice, we're converting it from analog to a digital representation. That's what's transmitted. It's essentially ones and zeros. And then at the back end, I take those digital bits, ones and zeros, and I convert them back to analog. Because unfortunately, we're still in lead space, right? We still live, we live in an analog world. Unless you watch The Matrix, where they plug into the back of your head, which is really cool, right? I guess maybe that's a digital world. I'm not sure. But good question. So I hope that answered. Yes, question?
Yeah. When you talk about Wi-Fi bands, like you had feature 2.1, A, B, G, and A,
Yep.
What is the difference between those bands?
Yeah, so the other question is if you dig a little deeper into Wi-Fi, there's the 802.11. So the 802.11 is a specification from a group called the IEEE. And then there's 802.A.B.G. The A just represents what frequency band. So I think the A is at 5.6 gigahertz, and there's certain tricks for modulation up there. The B, I believe, is at 2.4 gigahertz, and I think the G is also at 2.4 gigahertz. So it's just a specific standard on how we're going to negotiate, how we're going to communicate. I have my bits. I got to send them from point A to point B. How do I get them there? And it's just, how I take those bits and put it onto the sine wave is really a spec. But it is a great question. All right, so I'm switching back to the keys. I had the other question, right? So we did the birds. I have one more question for you. We still have about 8 more minutes. So let me go back to... all right, so where am I? I want to make sure everything's on. Power supply. All right, so I'm back to the CW case before. So this is it's a 915 megahertz sine wave. There's no information on it. It's just blasting out of this white antenna here and sending it into the environment. So right now it's working effectively like a radar. I'm the target. The energy's coming off the antenna, and it's bouncing off of me. You're seeing some change as I move around, because I'm changing my distance, my hands are going. You see some changes. So here was the question about the keys. Can your keys communicate? So obviously they can communicate, you can hear them, right? And so I can have them transmit, in this case, sound pressure waves. So it's still a sinusoidal waveform, and you can hear that. But I'm more interested, from an electronics point of view, how do I do this wirelessly? So this is where I'm going to go into what's called a backscatter mode. I'm just going to jingle the keys in front of the transmitter, and I'm going to receive it off the same one, and you can see some pretty fast changes here, and that doesn't look like data, but if I was to jingle them at a certain rate, I could represent ones and zeros as I do this. So the answer to the question is, yeah, your keys can communicate, sort of, but the more interesting thing, though, is really let's look at an RFID tag. So this is the things you're carrying around. I think someone pointed out smartly that we all have RFID tags with us. So I have another one here. The tags that you carry are designed for lower frequencies. So you're carrying a tag that has about 125 kilohertz sine waves. That's the communication. And as a result of that, you only get read distances of a few inches. Right? You have to get your tag pretty close to the guard's black box to get that thing to actually beep for you, right? To successfully go in. I know some of you probably like, yeah, it's close enough, no beep, I'm in. Right? And I think, unfortunately, some of the guards, they're checking Instagram, I guess, or MySpace. But this particular tag here, at a much higher frequency, uses a different type of antenna structure, and I can get tag reads out of this about 5 feet or 10 feet. Now that would be great, because that means you could just walk into the building And if I use this technology, I can actually read your tag in your bag, in your pocket, in your wallet. You don't even have to take it out. So that's the type of technology I'm going to use here. So if I push this in front of the system, we should start to see digital data. So what we're seeing there are the zeros, logic zeros are sitting down at 0 volts, very low amplitude, and the logic ones are sitting up much higher. I can zoom in on here so you can see there are your ones and zeros. So every time you see a pulse, that represents a 1 and a 0. I can scan through this. You can see in the beginning there's a set series of numbers, ones and zeros, and then I can scan through and you can see that there's bigger changes towards the end. So what we're seeing here out of this particular code is 128 bits. I can change those 128 ones and zeros into a number, and then I can associate the number with maybe whatever I attach this to. So this is what's called UHF RFID. Really good application for this is Walmart. I'm sure most of you shop at Walmart. When Walmart gets a delivery of product to their warehouse, 10 years ago, someone had to come with a handheld barcode scanner and scan every single box that's, let's say, on the pallet that the forklift is bringing in off the truck. Every single one was scanned. Walmart is all about low prices, as you know. I'm sure they drum that into you, right? All the commercials says we have the lowest prices. Well, how do they have the lowest prices? They come up with technologies that effectively remove the human element. So how do I eliminate the job of someone having to physically scan every box? And what they did is they switched to these types of tags. And now as the forklift comes into the building off the truck, I automatically read every single barcode, every single ID wirelessly, and I no longer need someone to scan that. So from an efficiency point of view, from a cost point of view, that's the structure we're using. So that's the application for this. The problem with this, though, to replace your ID cards, is there's a lot of people walking in the door. I would read 10 tags, and it's kind of hard to see, are there 10 people there or 11 people there? It's called singulation. I need to singulate down to the individual. That's why we still use the technology that's much closer reads. That's why we don't want this type of technology at our entrances, because someone could sneak in with a big crowd. I would read everybody. I would read the 10 that's supposed to be there. It's possible that one can sneak in. So that makes sense? So I'll leave you with the one last application. And so another good application for this is, but let's say there's a fire, and you're all running out the door. You're not scanning your badge as you're running out the door. If you had one of these in your pocket, I can actually identify that you're leaving, so that if the firemen come and we have to make sure that everyone's here, want to make sure Jack is still in the bathroom. If I don't have his tag leaving the building, then I can send the fireman in and say, we know Jack likes to hang out in the second floor bathroom. We can have him go right into that bathroom. Was that true or no? No, it's not true. It's not true. Don't spread that. Don't post that everywhere. I'll get in trouble. So again, that's the application. So I'll leave you with one thing. You said we're going 145. Yeah. Okay. So I just want to switch back to the different types of careers that the electrical engineer can have, and then we'll get you out of here. So we talked about a lot of different technologies today. Yeah, enough stage coming up. All right, so I'll end here. So I do appreciate you coming, taking the time, not doing too much posting.